Problems on pH and hydrolysis. Here is a problem for you. How many grams of sodium cyanide is required to prepare 1.25 liters of a solution with a pH of 7.8? Ka for HCN is 4.9 into 10 to the power of negative 10. So you're supposed to find out the amount of sodium cyanide needed to prepare 1.25 liters of the solution so that the pH would be 7.8. See what we can do here. Before we start, we need some equations in order to solve this problem. We'll just review them. The first one is Kw is equals to Ka into Kb. Second one is Kw is equals to H positive into OH minus. H positive is equals to 10 to the power of negative pH. Kb is equals to concentration of HCN into OH minus by HCN. When you write the hydrolysis of the strong conjugate base, which is Cn minus, this is the equation for the Kb expression. NaCN is a salt of a weak acid. Therefore, Cn minus is a strong conjugate base. We need all of this information before we could start to solve this problem. First, we will write the hydrolysis because Cn minus is a strong conjugate base. It is actually coming from the weak acid HCN. HCN is a weak acid, and Cn minus is coming from NaCN, which is a salt of a weak acid. Therefore, Cn minus is a strong conjugate base and it will undergo hydrolysis. So Cn minus plus H2O gives you HCN plus OH minus. This is the equation representing the hydrolysis of Cn minus. The dissociation constant for the hydrolysis in this case is Kb, as one of the products is a base. Kb is equals to HCN into OH minus divided by Cn minus. But in the question, we are not given the Kb value. Make note of that. Let's make an ice table. The ice table for the hydrolysis, the initial concentration of Cn minus, which is Y. This is the compound. NaCN has to be dissolved in water, 1.25 liters, to produce Cn minus. And we do not know the quantity. So Y is the unknown. We have to solve for Y. Change in concentration minus X, X, and X. And mind you, the X also represents the hydroxide ion concentration. And you are not given the pOH, but you're given the pH. And from the pH, you can calculate the hydrogen ion concentration and then convert it to the hydroxide ion concentration. That's what you have to do next. In the equilibrium expression, we have Y minus X, X, and X. So calculate the OH minus ions from the pH of the solution. So H positive is equals to 10 to the power of negative pH, which is 10 to the power of negative 7.8, which is equals to 1.5 into 10 to the power of negative 8. We may also proceed in an alternate route because pOH is equals to 14 minus pH. That will give you pOH is equals to 14.0 minus 7.8. That'll be 6.2, which means the OH minus ion concentration is equals to 10 to the power of negative pOH. We may also use this, but I'm using an alternate method where I'm going to use Kw is equals to H positive into OH minus. H positive is equals to 10 to the power of negative pH, which is equals to 10 to the power of negative 7.8, which is 1.5 into 10 to the power of negative 8 m. Kw is equals to H positive into OH minus. I'm going to rearrange that equation to write OH minus is equals to Kw by H positive. Kw is a constant, is an ion product of water, is 10 to the power of negative 14. Substituting the values, we get OH minus ion concentration is 6.6 into 10 to the power of negative 7 moles per liter. This is also equal to the value of X in the ice table. Second, we have to calculate the value of Kb. We already calculated the hydroxide ion concentration. Now we're going to calculate the value of Kb. And Kb is related to Kw like this. Kw is equals to Ka into Kb. We know Kw, we are given Ka, so we can find out Kb. Kb is equals to Kw by Ka. And Kb is equals to Kw is 1 into 10 to the power of negative 14. And Ka is 4.9 into 10 to the power of negative 10. And we have the Kb value here. And that's what we're going to use in the next slide. Hydrolysis of NaCN. Again, we already know the ice table that we generated earlier. We're going to write the equilibrium constant expression. Kb is equals to HCN into OH minus divided by Cn minus. X represents the concentration of the hydroxide ions, which we already calculated here. And if you substitute those values, you should get the final answer of Kb, or rather Y. So Kb is equals to, because we have HCN and OH, which is X and X, we can write Kb is equals to X squared by Y minus X. The value of X is going to be very small because Kb, when you calculate or when you look at the value of Kb, it's going to be extremely small, which we had seen in the previous slide. So we are going to make an assumption Y minus X is going to be equal to Y. Therefore, it's based on the fact that Kb is 2 into 10 to the power of negative 5. Now substituting the values, Kb is equal to HCN into OH minus divided by Cn minus. So Kb is 2.2 into 10 to the power of negative 5 is Kb. HCN and OH minus ion concentrations are there. Y is the unknown. We're going to solve for Y. In order to do that, we're going to rearrange the equation. Y is equals to 6.6 into 10 to the power of negative 2, the whole square divided by 2 into 10 to the power of negative 5. So Y also represents the concentration of the cyanide ions, which is also equivalent to the concentration of sodium cyanide that we need in order to produce the same concentration. So Y is equals to 2.1 into 10 to the power of negative 8 moles per liter is the concentration of sodium cyanide that we need in 1 liter, because it is per liter here. Converting molarity to grams per liter. Moles is equals to mass over molar mass. Mass is equals to moles times molar mass. So mass of NaCN is equals to moles of sodium cyanide in 1 liter times the molar mass, which is 49 grams per mole. The value is 1.067 into 10 to the power of negative 6 grams in 1 liter. Now, since we need 1.25 liters, the mass of NaCN in 1.25 liters would be obtained by multiplying the value by 1.25. So the final answer is going to be 1.067 into 10 to the power of negative 6 grams of NaCN is required to prepare 1.25 liters of the solution having a pH of 7.8. And mind you, 7.8 means the solution is basic, and sodium cyanide has a strong conjugate base. Making the solution basic or increasing the pH is an agreement with a theoretical understanding of hydrolysis of strong conjugate bases. That's it for now.